quantum algorithms and near-term quantum computing. Excuse me. Whenever you're ready, Marco.
Thank you very much. Thanks for the invitation, and thanks for everyone that is here to listen to this talk. Today, I'm going to be talking about some of the work that we've been doing about variational algorithms for estimating the quantum feature information and overall for sensing in general. I don't know if you can see this thing up here. I might try to put it down here so that it doesn't bother you all. All right, so what is it? This is a little bit of the outline of what I'm going to be talking about. I'm going to be introducing quantum sensing and more generally the quantum feature information and why we care about it. We're going to present some of the results on providing bounds for the quantum feature information and why those are important. And then a variational quantum algorithm that we can use along with those bounds to estimate the quantum feature information and prepare good quantum states for quantum sensing. And then I'm just going to give some conclusions and outlook. So first of all, why do we care about quantum sensing, right? We know that we have a lot of really good classical devices for sensing, and quantum systems, they have this thing that in principle, we can think about them as being extremely sensitive to their environment, right? So they decohere very fast. And this is one of the main challenges for near-term quantum computing, where we're trying to take quantum computers and we're just trying to control and tame those interactions between the qubits and the environment, which make you lose information, right? But on the other hand, we also know that this extreme sensitivity that qubits and quantum systems have in general to interact with their environment can be very good, because that's precisely what we want to try to do in quantum sensing, right? We want to try to leverage this high sensitivity of quantum systems for some practical task. And in principle, this task, we can just frame it as we want to take a quantum system, we want to make it interact with its environment and try to learn something about the environment by looking at the quantum system, right? So this is the general framework that we're going to be working in. And it's been shown that if you try to use quantum systems for sensing and trying to extract information about your environment by exploiting properties such as superposition and entanglement, you can actually overcome the sensitivity of classical systems, right? So this is the ultimate goal. And quantum systems and quantum sensors have been proposed and are being used for measuring properties of magnetic materials, detecting gravitational waves, studying dark matter. So there is a plethora of things that we can do with quantum sensors, right? But of course, as we said, we want to try to make sure that we have a good quantum system that interacts with the environment in the way that we want it to interact, so that it does it in the most controlled fashion so that we can get the best information out of it, right? So for now, let's talk about this thing, the quantum feature information, and let's just present a general scenario where what we have is a quantum system rho. What we're going to do is that we're going to make it interact with a source that is going to encode some parameter into this quantum state. That parameter can be a magnetic field, it can be a temperature, it can be a gravitational field, whatever. And what we want is to try to measure our quantum state and try to get an estimation of the encoded parameter with a good sensitivity, right? We want to have it such that small changes in the parameters can be detected with our quantum state rho, because that's what we want, right? We want high sensitivity. And what we know is that the sensitivity of a quantum state to be used as a quantum sensor is ultimately bounded by what is called as the quantum parameter-Rao bound right here. Where here you can think about how much our parameter is going to change, how sensitive is my state to changes in the parameter, and this is lower bounded by this quantity right here, and this is the quantum feature information, right? And this is an information theoretical limit for how good a quantum system can be as a sensor. And now we have this formula for the quantum feature information. You can think about it in the following way. First, let's try to understand the different terms that go into here. Here you see that there's a limit of this quantity delta going to 0. And here we have this F right here, which is the fidelity. So this is the fidelity between two states. The first state is going to be the exact state, which we usually call, which is take your quantum state and, for instance, make it interact with a source that just rotates around some generator Hamiltonian G and encodes this parameter theta in your quantum state, right? Then we have here what is called the error state, which is take your parameter, but rotate it just a little bit further, right? So you're trying to compare how sensitive is your state to a rotation rho, a rotation theta, and a rotation theta plus delta, right? And this quantity F is, of course, the fidelity, the quantum fidelity. And what this quantity right here is telling us is how much is my state changing whenever I go from theta to theta plus delta. Evidently, what we want is to have a state that whenever I apply the small change delta, my state changes significantly, right? So the fidelity decays. And this is really good because this means that my state is very sensitive to this small change delta. On the other hand, if those two states are exactly the same, for instance, my state rho is completely unaware that instead of doing theta, I did delta, and those two states are the same, the fidelity is 1, and I'm going to get 0 quantum feature information, right? So this is just going to blow up, and we don't want this. So this is a quantity, and this is what is going to be the main interest for us, because this is going to be how we quantify how good a quantum state is for being used as a sensor, right? To this quantity called the quantum feature information. But of course, you know, the problem with the quantum feature information, there's several technical things, right? First, we had this limit of delta going to 0. So the first thing that we're going to say is that we're just going to take a finite delta, and we're just going to look at this finite quantity right here, right? This is what we can potentially study in an experiment, right? This small delta is however much we can interact with our quantum state by turning the knob of the interaction with the parameter that we're trying to control. But most importantly is that if we want to try to compute this fidelity through a quantum computer, we're generally going to have a problem because the fidelity is a nonlinear quantity of the matrix elements of my density matrix rho. So the fidelity, of course, becomes the overlap for pure states, but we all know that in practice, quantum systems and quantum technologies are not ideal. You're not going to have pure states, you're going to have mixed states, and the fidelity for mixed states is not as trivial to compute, right? So if rho theta and rho theta plus delta are two mixed states, we're going to have the problem that we need to compute this quantity right here. And because this is a nonlinear quantity of the matrix elements of rho, there is no quantum algorithm that is capable of exactly computing the fidelity, right? Because it's, again, a nonlinear quantity in the matrix elements of rho. So we might have ways of approximating this fidelity, for instance, via Taylor series expansion or whatnot, but those are essentially going to be expensive to compute, right? And maybe we don't want to go there. So the next thing that we're trying to do is how can we still try to use the quantum feature information? I'm just going to move this for a second. And the main idea is that if we cannot compute the quantum feature information, maybe we can bound it. And maybe we can use bounds on the quantum feature information to try to, bounds on the fidelity and hence on the quantum feature information to use those as proxies, right? Because our goal, as we said, is that we want to try to maximize the quantum feature information. This minimizes the error in estimating my parameter. And if I have a lower bound for the quantum feature information and I maximize this lower bound, I have a guarantee that my QFI is larger, right? So this is why we're going to be talking about bounds on the quantum feature information. So here, as we said, if we cannot compute the quantum feature information, let's try to bound it, right? So we introduced this quantity, which we call the sub-quantum feature information, and it's introduced as this quantity right here, which is very similar to the previous equation that we had for the quantum feature information. But instead of the F, now we have this G right here, and this G is actually an upper bound for the fidelity. And this upper bound is called the super fidelity. And the super fidelity is given by this equation right here. Now you can see that this has some really nice properties because you take your exact state, you take your error state, and now you just have to compute their overlap and you have to compute the respective purity of those two states. And those can be efficiently computed in a quantum computer, right? We can actually do this with a depth 2 circuit and some post-processing via this paper that is right here. So this is something that we can efficiently compute. So we got rid of this problem that we cannot compute the fidelity, right? And the next thing that we know is that because this is an upper bound for the fidelity, this quantity right here is always a lower bound for our true quantum feature information, right? So this is a strict bound. And what we were able to prove is that the sub-quantum feature information actually has some really nice properties that makes it a very faithful lower bound for the actual quantum feature information. So for instance, the first thing that we proved is that they share the same global extrema. So what this means is that if the quantum feature information is 0, the sub-quantum feature information is 0. This is kind of trivial to prove. The most complicated one and the more interesting one is that they actually share the same optimal state. So if you can prepare the best state that maximizes the quantum feature information, and this is actually the state that you want to use as a quantum sensor because it's extremely sensitive to changes in your parameter, it's also going to maximize the sub-quantum feature information. So this makes it such that if we work with the sub-quantum feature information, we have good reasons to believe that if we optimize the sub-quantum feature information, we're going to get a good state for quantum sensing. So this is the main idea. Let's go back to the original setting where we have our quantum state that has some parameter encoded in it. We're going to send this in a quantum computer where we can use, for instance, this is the actual circuit that I was telling, the depth 2 circuit that can compute the trace of rho sigma. And what we're going to do is, because we cannot use the quantum feature information, as this is not efficiently computable, we compute the sub-quantum feature information, and we just try to find the state that optimizes the sub-QFI, because we have the guarantee that they share the same optimal state, right? So we're going to use the sub-QFI as a proxy for the QFI. So now let's talk about how we're going to actually do this, right? So we already know that the current quantum devices that we have, those NIST quantum devices, are still in their infancy. They're noisy, they have a limited number of qubits, they have a limited connectivity, and that means that the things that we can do with them is quite limited, but we still can do some stuff with them. So for instance, one of the main and leading approaches to make use of near-term quantum computers are variational quantum algorithms or quantum machine learning schemes, right? And here the main idea is that you have a problem, you're going to define a cost function that you're going to be trying to minimize, you're going to have some way to process information with an ansatz, for instance, for a parameterized quantum circuit or quantum neural network. And the goal is to try to use both quantum and classical computers. In the quantum computer, we're going to take quantum states, send them through a quantum circuit and do some measurements. And from those measurements, we're going to build a cost function that we're going to try to optimize. The cost function usually encodes the problem at hand. And their goal is to try to find the set of parameters, for instance, in a parameterized quantum circuit that minimizes this cost function, right? So that's going to be done by a classical computer, which is going to take the value of the cost function at a given iteration step, and is going to tell us you should update your parameters in this way such that your cost is going to be minimized, right? So you get this optimization loop between a quantum and a classical computer. And of course, then, the output of this variational algorithm depends on the problem at hand. In our case, our output is going to be the quantum state that we want to use as a good quantum sensor, right? So this is where we introduce this algorithm, which we call the variational quantum feature estimation algorithm. It is a mouthful, I know, but the main idea is that this is an algorithm that takes as input a quantum state, and this is, an easy to prepare quantum state. Think about the old 0 state. And the idea is that you want to try to take this state, you want to send it through a parameterized quantum circuit, which is this U of alpha that is right here. And the goal of U alpha is to prepare a good quantum state to use as a sensor, right? So this right here is the probe state that we previously had. So once we have the state, we encode the parameter theta, we encode the parameter theta plus delta. We compute, for instance, the sub-quantum feature information. We have also other bounds that we have proposed for the QFI, which I'm not going to get into the detail for. And once we have those bounds, we are just going to train the parameters in this U of alpha such that the lower bound get maximized. Because we know that if we maximize our lower bound, we are also maximizing the quantum feature information, right? And we just do this loop until we reach convergence, and we have a guarantee that we have a good quantum state for a given sensing algorithm, right? And what's really nice about this is that we don't really need to know a lot of information. So for instance, this thing right here, how the parameter is encoded into my state, it can be a black box. I do not require this information to be able to prepare a good quantum state for quantum sensing. And this is a non-trivial statement, right? Because usually whenever you think about sensing, right, you think about magnetometry. What's the optimal state? It's the GHZ state. But how do you know that the GHZ state is the optimal state? Well, because you have a lot of information about the problem. You know how the parameter is encoded. You know that there is no noise. You have a lot of information that you can use to reach that conclusion that GHZ is the optimal state. But if you don't have any of that information, if this is a black box, then you cannot get general theoretical results. And hence, this is why such a problem agnostic approach can be very useful. So very quickly, just to wrap things up, this is one of the numerical results where we have, we're trying to optimize our lower bound, which is going to be our bounds on the quantum feature information. And you can see that as the number of iterations increases and we train the circuit that prepares a good quantum state, the lower bound for the quantum feature information increases as expected. And we can try this for different purities. This is related to another type of bounds that we have. But overall, the idea is that we can show that we can reach almost the absolute maximum, or in some cases, the absolute maximum that is capable for a given quantum state with a given purity, right? So whenever you don't have pure states, GHZ is no longer the optimal state. There is another state that is the optimal mixed state. So the best that we can do is this green line. And you can see that we can get pretty close with this. So we can prepare good quantum states without any information about the task at hand. And the other thing that we did is that the only bound that we knew for the quantum feature information, the only lower bound was this thing right here. And we can prove that our bounds, we have lower and upper bounds, so that now we can get an exact range where the quantum feature information lives, are much, much tighter than previously known bounds in the literature. So this shows that this approach that we're taking and the bounds that we have are definitely more operationally meaningful than this quantity right here. For instance, here we know in this case that the quantum feature information lies somewhere between this purple and blue line because we have a lower and an upper bound that are strict. And here you can see that the known lower bound that people were using in the literature to train over is actually quite bad. So optimizing this doesn't give you a guarantee that you have an actual good quantum state. So with that, I want to thank you all for your attention and just say that our results are that we proposed a novel algorithm for computing the quantum feature information. We can use this algorithm along with our bounds to prepare good quantum states. And then the next steps that we're considering is how can we create good ansatz for quantum circuits, right? For sensing, what is that structure of that trainable circuit? And how can we do, for instance, multi-parameter estimation? Here we're just considering single parameter estimation. So, there's definitely a lot of interesting things to do. And I just want to thank my collaborators and all of you for listening to this talk. Thank you very much.
Thank you, Mark. Thank you, Marco. Are there any questions from the audience? Otherwise, I have a question about your, and I think you might have touched this on the last slide, but you talked a lot about the upper or the lower bound, but in some of your earlier slides, you showed that all the global extremas match. Is that what you're discussing here in this last, did you use that that extra information of lower bounds and upper bounds in this one, or is this other people's works and you're going to continue with the sub QFI for upper?
Right. So those bounds, everything here except the orange ones are bounds that we propose, both lower and upper bounds. But the thing about the upper bound is that we cannot use the upper bound for training because, minimizing the lower bound doesn't really tell you about anything about where the quantum feature information lives. You can have a lower bound that is quite small, but a quantum feature information that is even smaller. So that's why mainly I was focusing on the lower bounds. The upper bounds are actually used to give us an actual range, right? So you've minimized your lower bound and you're like, right, but where is my quantum feature information? I just know that it's above this value. So the lower bound helps to put a range here. It's not that useful for the training part, but it is useful to get an accurate estimate of where your quantum feature information lives, right? And I didn't get into the detail because, as you can see here, we proposed 4 bounds, 2 lower and 2 upper, and I didn't want to bore you all with formulas and mathematical equations.
Thanks. We'll thank our speaker one more time. And our next speaker is Matthew Feldman. Matthew Feldman is postdoc research associate at Oak Ridge National Laboratory, where he focuses on continuous variable quantum optics, quantum machine learning in the effort to develop state-of-the-art quantum sensors. Go ahead, Matthew.
Sorry about that, I was muted.
We can hear you now.
Great. And okay, well, I guess I'm having technical difficulties with my video. Oh, thank you for the introduction, and I will be discussing two-mode squeeze light resource for quantum compiling. And so I've just started my position here at Oak Ridge National Lab for the past about 6 or 7 months ago. And the motivation for this work that I'll be discussing really goes back to some of the stuff that Andrew Schonberger was discussing earlier today. So if you remembered, he's spoken about these continuous variable quantum mechanics compiler systems where you could exploit squeezing gates and entangling gates as, or I guess superposition gates, which generate entanglement gates, basically as a resource to speed up quantum compilations. And the way that essentially works is just as a reminder, you have some unitary that we're trying to compile or learn. And we have some subsystem in here, VDagger, that has a sufficient number of parameters to learn that unitary. And basically, you can use entanglement essentially as a resource to reduce the size of your training data set, where that size essentially is this absolute value of S, which is the number of training data pairs. And so basically the error between the our target unitary U and the simulated VDagger that we're learning or that we're optimizing to learn U has some mean error, which is given by this NFL or no free lunch column here, where this first one is an unentangled or separable, is using separable states, whereas the other two are using entangled states for the quantum compiler or simulator. And so what you'll notice is there's actually this Schmidt rank term in both of these that basically amounts to how entangled the compiler system is that you're using to learn U. And essentially that's a knob you can dial to reduce the training data set and speed up your calculation. So that's the motivation. And then in terms of, when we were looking through this paper, we thought, oh, well, we make entangled and squeezed light sources on a regular basis in our lab, so we should definitely try this. And so we reached out to Andrew and company, Tyler Volkoff and Zoe Holmes, and to talk to them about their great work that was published in this PRX Quantum, and basically try and build it in the lab. So essentially, we to implement this, one large part of the step is actually implement a squeeze light source that has interferometric readout. So in our lab, what we do is we use four-wave mixing by basically heating up a rubidium to form a rubidium vapor. And when you do that, you create this lambda configuration, as shown here, where the excited states, the four or so excited states, are essentially blurred and make one excited state. And if you pump sufficiently off resonance and also have a probe seed to excite this lambda configuration, you can meet the conditions for four-way mixing. This essentially generates becomes a nonlinear gain medium, and you pump in two photons, you get two photons out, a probe photon and a conjugate photon. And these photons are twin beams, meaning that they're entangled. And also they generate squeezing between the sum or difference of their quadratures, either their amplitude or phase. Different sums or differences, or actually differences or sums, respectively. And so to do this in the lab, what we do is we have a tunable laser to generate our pump. So then we create our pump mode. Then we pick off some of the pump to pass it through an AOM to essentially pass that light and modulate it up by about 3 gigahertz to meet this energy difference here to properly meet the forward mixing conditions. And then we pass that into the rubidium vapor cell, combining them using polarizer and beam splitters. And you're at the right temperature, and voila, you have four-way mixing. And with a little bit of of work, you can get the right conditions for squeezing by sweeping the temperature as well as the laser frequency and minimizing losses, etc. And you can read all of this out using a standard homodyne interferometry, where you have a local oscillator that you interfere with both the conjugate and the probe. And then you can look at the sums or the differences of those signals after they have been down converted into currents through a balance detector. And so basically the quadratures that we're measuring are since this is 2-mode squeeze light, we're looking at phase sums and amplitude differences. And they are going to be respectively squeezed and anti-squeezed. And that will vary as you vary the local oscillator phase, or respectively as you vary the squeezing as a function of time. And we can see that, like here in green, we're looking at the phase sum. Here is anti-squeezed, and the amplitude difference is, the phase sum is squeezed rather, and the amplitude difference is anti-squeezed. And this is all relative to the blue and red lines, which are the shot noise limit. And this is great and all, but there's actually like some other steps that we sort of skipped over that we should check. And we want to confirm that we have sufficient squeezing before we get to a more complicated measurement readout. And to do that, you have a simpler measurement scheme where you just pass the light from these entangled beams, the conjugate and probe, onto a balance detector. You look at the intensity difference. This is a balance detector. You're taking the difference of the two intensities. You read it out on a signal analyzer, and you can actually see you can actually plot the sum of the intensities of the probe and the conjugate as you vary their the input power to the squeeze light source, and against the noise power for a given input laser power. And we can see that for the squeeze case, or the quantum case rather, which is shown in green, that the noise floor is most definitely well below the classical or shot noise limited case. And we actually can take a ratio of these rates here of these fits and convert it to log or to a decibel scale, and you'll see that you get about 5 dB of squeezing. And correspondingly, we also want to look at what the spectral properties of the squeezing are as well. So, because our signal could reside somewhere across the RF domain for various types of, signals of interest. And so we, again, measure the classical limit and then compare it to the squeezed case, which is in blue, and we can see that we're squeezed. We also confirm that by taking the difference and looking at the actual squeezing value, which is around 5 dB again. And so this is basically the starting point where we're at. And the next steps are essentially we want to just go ahead and build the full interferometer system that Andrew and company have mentioned to sort of exploit this quantum compilation scheme. And to do that, we essentially make the interferometer that I just shown previous few slides ago, but we actually extend that to a SU11 interferometer. So we actually have two. Instead of like a linear interferometer, for example, where you'd have beam splitters here, you would just place them in the parametric amplifiers. And then you have basically a squeezing gate, as well as an entanglement gate, and also an unentanglement and unsqueezing gate. And we can put a unitary that's well understood, maybe something that provides a phase shift, have appropriate degrees of freedom to have essentially a V dagger over here to learn that unitary. And then we will apply variational quantum algorithms and be working with Andrew and company to have a proof of principle in the lab for the scheme. And so with that, I'd just like to thank my advisor, Raphael Puzer, and also mention my lab mates who I'm working with on various projects here at the lab, Song Jin, Hong, and Claire Marvini. And also our collaborators, Andrew, Tyler Volkov, and Zoe Holmes, who are all on the theory side of these things. Thank you for your time. And also thank you to the Quantum Science Center for the funding for this new project.
Thanks, Matthew, for the talk. It's really exciting, and I'm excited to see what comes out of it. Do you have any plans for what system you're going to put as your unitary
Yeah, I think I think I think probably simple and interesting. So that would be the best thing to do. So, and I don't know that that's going to be a single thing. There's probably maybe two things. Maybe you have something that just applies a simple phase shift, like a piece of glass or a dielectric medium or something like that. And that'll be a simple calibration. And then maybe put an interferometer within an interferometer or something along those lines. Maybe look into something that has like a Kerr effect. But I think starting simpler probably makes sense as a calibration first.
All right, thanks. Are there any other questions from the audience? If not, let's thank our speaker one more time. And we'll welcome our next speaker. Our next speaker is Alex Sinichev. Alex Sinichev is a postdoc at the university, research associate at Elmore Family School of Electrical and Computer Engineering at Purdue University. And he works with quantum nanophotonics for engineering solid state quantum emitters. Welcome, Alex.
Thank you. My name is Alex Sinichev. I'm a postdoc here at Purdue University, and I work in the group of Professor Alexander Baltaseva and Vladimir Shalayev. And today I would like to give you a short presentation about our research on integration of solid-state single photon emitters in silicon nitride photonic platform. This work is a result of team effort of our grad students and postdocs, and I would like to specifically mention the contribution of our grad students, Sam Piana, Omer Yesharyud, and Zach Martin. We also collaborate on this work with Oak Ridge National Laboratory through the Quantum Science Center. All right. Try again. All right. All right. Integration of quantum emitters. First of all, solid-state quantum emitters is an essential building block for integrated quantum photonic applications. Quantum emitters, solid-state quantum emitters, they have a potential to provide on-demand, efficient sources of indistinguishable photons, which is an essential resource for quantum computing. Moreover, solid-state quantum emitters, they allow integrations with on-chip photonic circuitry, which is particularly important for scalability of these devices. So there are generally two approaches to integrate solid-state quantum emitters with a photonic circuitry. One is a monolithic approach, where you use materials with intrinsic quantum emitters, and you use these materials for fabrication of waveguides and photonic crystals, or you use a hybrid approach where you have materials with quantum emitters and materials suitable for the fabrication of the full-fledged photonic circuitry, and you combine these two dissimilar materials. One of the key figures of merit of these integrated devices is the coupling efficiency. So the coupling efficiency is the probability of an emitted photon to be channeled in the desired waveguide mode. And generally, coupling efficiency depends on different parameters, on the refractive index of the material, on the integration schemes, on the footprint of the device. And for example, if we simply put a material hosting quantum emitters on top of the waveguide, from the simulation, we can expect for a thick material, the coupling efficiency on the level of a few percent, and up to 15% for two-dimensional materials when we have quantum emitters close to the interface with waveguides. The coupling efficiency can be further improved if you use some other approaches, for example, encapsulation. So you can encapsulate material hosting quantum emitters into the waveguide material, and then you can expect from the simulation up to 20% coupling efficiency. And even higher coupling efficiency is expected from intrinsic quantum emitters. So intrinsic meaning that you have emitters in the material that itself you use for the fabrication of waveguides. For example, I can show here in our group, we have recently discovered the formation of solid state single photon emitters in silicon nitride, which is an excellent photonic material platform. And we attempted also the first integration of such emitters with planar waveguides. However, for most of the practical quantum photonic applications, near unity coupling efficiency is essential. And to even further increase the coupling efficiency from of the photons from emitters to the waveguide, we can use different techniques. And for example, we can use inverse design optimization framework, namely topology optimization, to channel all the emission from quantum emitters to the waveguide mode. Here's an example. I would like to show you the work, the simulation work by our grad student Omer Yeşilyurt, where this technique is applied. So inverse design approaches are techniques to algorithmic techniques that help to discover material structure or structure of optical materials based on desired functional characteristics. And how does this work? For example, in this work, there was waveguide made of a silicon nitride, and there was selected an optimization area where you place on top material hosting quantum emitters. And then what you do next, you iteratively structure this material to change the environment and channel all the emission emitted from the source to the waveguide mode. The optimization starts from the random smooth distribution of the material, as it's shown on the figure, and then at each step, it changes up till and converges to the binary distribution of the material. Binary meaning that there are areas where we have material and areas where we simply don't have material. And this is basically the structure that can be practically fabricated. And using this approach, we would wanted in our project to experimentally demonstrate the coupling of quantum emitters in different materials to the waveguide through such topology optimized couplers. So first we start with the material platform. So we used the silicon nitride as a photonic material platform, since silicon nitride is a well-known platform for photonic integrated circuits, is well developed and has low losses. So, but in our work, we also used a special type of silicon nitride. We use nitrogen-rich silicon nitride, so grown by high-density plasma chemical vapor deposition technique. So when we increase the nitrogen content in silicon nitride, we can substantially suppress the autofluorescence of silicon nitride, which is typical for the conventional stoichiometric one. And this is particularly important for interfacing with quantum emitters that emit photons in the same spectral range. However, with the increase of the nitrogen content in our material, we also observe the decrease of the refractive index. And however, at the current stage of our project is the necessary trade-off that we take to accept to obtain low autofluorescence silicon nitride. And low refractive index means that you have less tight confinement of the optical modes and you will have more losses. But in our work, having this now low autofluorescence silicon nitride established, we studied different approaches to combine this material or integrate with different materials hosting quantum emitters. For example, we considered in our work nanodiamonds with NV centers, which are the most studied and most promising quantum emitters for applications. We also studied hexagonal boron defects and hexagonal boron nitride. And as I mentioned earlier, that since we discovered in this low autofluorescence silicon nitride intrinsic quantum emitters, we also considered the ways to integrate them efficiently with integrated photonic security. But here I would like to give you just an example of our work with HBN. So here I show you my optical microscopy image of the HBN on silicon dioxide substrate, which was thermally annealed to activate quantum emitters. Once we confirmed that there are single photon sources in this material, the HBN flakes were encapsulated into the low fluorescence silicon nitride. And then we were again probed for the photophysical properties of these emitters. And as you can see from the photoluminescence intensity map, we still observe isolated emitters, and by performing second order autocorrelation measurements, we can confirm that they are single photon emitters, and probing the spectrum, we still observe the same spectra that we would expect from this type of defects in HBN. So that means that at this point, we show that the encapsulation of HBN into the silicon nitride by HDP-CVD growth technique preserves their properties and doesn't change and can be used for further fabrication steps. So, and at the next step, we wanted to test the fabrication of these topology optimized couplers. And as you can see here, there's a first approach of the fabrication silicon nitride topology optimized couplers on silicon dioxide substrates. And the goal was here to test the structural quality, what we can attain in terms of the smallest features of these topology optimized couplers, and inform the simulation process on what restrictions should be applied or fabrication constraints for the next steps of the optimization. Because for the high efficiency, we can get at some point through the simulation the structure that cannot be practically fabricated using lithography techniques. So having now the material platform established and studied the encapsulation of the quantum emitters in silicon nitride and having tested the fabrication of topology optimized couplers, we now at the most challenging part of this approach is to place the emitter right at the right position within these topology optimized couplers. And as you can see from the scale bar, so this is the coupler is roughly 1 by 1 micrometer. So clearly we need the sub-diffraction limited precision to place these emitters within the optimized area. And this is a challenging technique, and we are developing now the procedures with alignment markers and mapping techniques so that we can, for example, in case of HBN, where the emitters typically are randomly distributed, we can localize very precisely these emitters within HBN and then use markers to position the mask from the lithography right at the position where we have emitters. Another approach would be, instead of localization of emitters from the measurements of randomly distributed, is to produce site-controlled quantum emitters in these materials. And there are works in HBN where people try different techniques to fabricate emitters at specific positions. Here also what we're exploring, since we discovered previously in our work the formation of intrinsic emitters in silicon nitride too, and this is work done mainly by now grad student Sam Piana, is now to deterministically fabricate site-controlled emitters at specific positions. So using the combination of alignment marks and this deterministic process of fabrication of emitters may simplify the alignment with the topology optimized couplers and ensure the high coupling efficiency expected from the simulation. This is ongoing effort, and I hope to very soon to present our new results and the real numbers from the coupling of single photon emission to the waveguide structure. At this, I would like to thank my co-authors and colleagues and all our wonderful group, and thank you to you for your attention. Thank you.
Thank you, Alex. Are there any questions?
I have a question.
I guess I do have one question about, so your simulations on your topologically optimized go to about 70% coupling efficiency on, I can't remember, slide 2 or 3. What's the next step to push it to 100%? Is there something that you can do next?
Thank you so much for this question. I would like to emphasize here that, yes, as I said, for real applications, we need coupling efficiency, near unity coupling efficiency. This is critical, especially when we scale the system, when the overall efficiency will quickly decrease. So here we have number 78%, which is already close to the number that would be interesting for the practical applications. And important to mention here that these numbers is obtained for the specific material set. So we use it, we have these numbers for silicon nitride with a refractive index 2. In case of stoichiometric one, in our case, it's even slightly less, and for HBN. So if we would use, for example, materials with high refractive index and would not be limited by the footprint of the optimized or of the coupling area on the chip, then the coupling efficiency would be significantly higher. So as was demonstrated, for example, for quantum dots in a photonic crystal waveguides. Yeah, so there is a room to improve this, for sure.
Thank you.
Thank you.
Any other questions? If not, we'll thank our speaker one more time.
I have a question. Hello?
Okay, and our next speaker is Kelly Stifter. Kelly is a postdoc at Fermi National Laboratory, where she works on quantum sensing mechanisms with quantum devices.
Thank you so much. All right, so I want to start with first a disclaimer. So I actually wasn't a recipient of one of these postdoc awards. The original award went to Noah Karinsky, but he has since moved into a permanent position at SLAC National Lab. And I was the fortunate inheritor of the award funds. So I have since assumed responsibility for the project in his stead. And today I'm excited to tell you about our progress towards building a scanning laser device for low energy characterization of cryogenic devices. So I first want to start with a big picture. I mean, in fact, the largest picture that you can imagine, that is our entire universe. So we know through a variety of astronomical measurements that all of the regular matter in the entire universe only accounts for 5% of the energy density in the universe. And we like to think we know a lot about that 5%, but the reality is that 95% of the universe, we don't understand very well. That's a little embarrassing for us astrophysicists and cosmologists. But we do know that 26% of the energy density of the universe is this stuff that we call dark matter. You'll notice that there's actually a lot more dark matter than there is regular matter. In fact, our galaxy is swimming in this sea of dark matter. We think that there's dark matter going through us, going through the Earth all the time, every day. And I really like how it's put in this quote here, that while the observational evidence for dark matter is exceptionally convincing, our current level of ignorance of the basic properties of dark matter is remarkable. And so why is that? Why do we know so little about the nature of dark matter? That's because we haven't yet detected it in the lab. This is because we think that it interacts with regular matter only very, very rarely. But on the rare occasion that it does interact with regular matter, we want to be able to see that interaction by developing detectors. And so here I'm showing it one particular detection scheme. To be clear, this is a detection scheme for particle dark matter rather than the wave-like dark matter that Aaron was talking about this morning. So the general idea here is that you have an individual dark matter particle and it comes in and scatters off of your detector substrate. And you can think of that very much as a billiard ball situation, billiard balls bouncing off one another. And in that interaction, there may be ionization charge that is produced. There may be phonons. And so then those ionization charges and phonons can propagate through your substrate up to sensors that you have patterned onto your substrate. So this is great. We do this and we still haven't seen anything. So what we'd really like to be able to do is push the boundaries of dark matter detection. And so right now, that means looking for low mass dark matter models, which produce only very, very small energy depositions in our substrate. So that means that we need sensors that can detect these very small energy depositions, which kind of naturally leads us to this world of quantum sensors, which are capable of doing such a thing. So when we think about these kind of overlapping fields of dark matter detection and quantum sensors, there's a whole host of open questions that have yet to be answered. And you can see that they really are overlapping. There are things that the individual fields are concerned about, but there are a number of things that we're both concerned about. But really, all of these questions have kind of this fundamental underlying thing of what is the sensing mechanism. So what we'd really like to be able to do is characterize our cryogenic devices with very small energy deposits. So our solution to this problem is a pulsed steerable laser beam that we can use with a wide variety of our cryogenic devices. And so that's what's pictured here. Let me walk you through it. So first you start with your light source of choice. It can be a wide range of potential wavelengths, so potential energies. You then collimate your light into a beam. And then you can actually chop the light into a pulsed beam. And so you do that using a rotating mirror. And you can actually sweep your beam across a narrow slit, and then you get a pulsed beam at the output of that slit. And you can filter your pulse beam and then inject it into a cryostat, where your cryogenic devices like to live. Shine it onto another rotating mirror and use that rotating mirror to actually steer your beam onto any desired 2D location on your device. And then those photons will produce energy deposits in your device at very specific locations. So this is very useful, and the concept is all well and good. Of course, it comes with its own set of technical challenges. Chief among them is cryogenic movement. So cryogenic movement is challenging because often for movement you have to put energy into a system. That means putting heat into a system, and so that's not so great if you're running a cryogenic device down at, say, 10 millikelvin. It's also potentially problematic because down at those very low temperatures, you will often freeze out your movement mechanism or your movement control. So our solution to this problem is to use modified MEMS mirrors, which a picture is shown there. So MEMS stands for micro electromechanical systems. And these MEMS mirrors are really nice for a variety of reasons. Some basic ones, right out of the box, they have really high broadband reflectance. So for a variety of wavelengths, it's just an aluminized surface. They give you relatively large deflection angles, and so you get to scan over a pretty large area. But what really makes it is that they don't dissipate power when they're stationary. And so you are not pumping a bunch of power into your fridge, which is great. We did have to work with the company. You can see the company name there is Miracle. We did have to work with them in order to ensure that these mirrors are going to be functional at these very low temperatures. The original design includes doped silicon control lines that would actually freeze out at low temperatures. And so we worked with the company to deposit a layer of aluminum over those control lines so that they will work at these low temperatures. So with this technology, we've developed this robust design. And so the idea here is that you have some focusing optics to collimate your beam down to a very small point. You then bounce your laser off of this steerable MEMS mirror. And then you kind of have this zigzag to a stationary mirror. That zigzag just helps you shorten the overall length of this unit because you're trying to put it into a very small dilution refrigerator. And then it goes to the output where you can attach your favorite cryogenic device. And using these MEMS mirrors gives us some really nice operating specifications. So we've seen that we get about 1.5 inches by 1.5 inches of scanning area. This is plenty large enough for most of the qubit or other device chips that are being used today. We've also measured about 100 micron beam spot size and think we can actually get down to about 50 microns. And this is useful because obviously these devices are very small. And so with this small spot size, you're able to target very specific pieces of your device. We're expecting about a 10 micron position resolution, so you have really excellent repeatability. You can scan across your device pretty quickly. You have a pretty small pulse width, and then all of these things you get at temperatures all the way from room temperature down to about 10 millikelvin. So where have we come so far? Oh, you can't see my labels there, but so the pictures I've been showing you are of actually this 3D printed plastic prototype that we have. So we've put the design together, we know that it works, and when we're actually waiting on the full copper version that is going to go into the fridge, should be delivered on Monday. Very exciting. In the meantime, we've been working on these warm characterization tests. So up in the upper right there, you can see a portion of the scanning area being traced out by a visible laser. And then on the bottom right, we've been testing everything to make sure that it's actually going to fit into the dilution refrigerator that we plan to run in. But looking forward, once we ensure that this device works, there are many possible science applications that this device can help with. So I show you this picture again because actually each item listed here can benefit from the application of this device. And I want to call out 4 in particular here because these are the 4 that we expect to be working on at Fermilab in the near term. But even beyond that, we are already planning to implement this scanning device in labs across the US. We know that we're going to make at least 10 copies of this device and potentially more as time goes on. So that's basically what I have today. The takeaways that I want to leave you with are that quantum sensors can help us push the boundaries of dark matter detection, that we've developed this really powerful tool to help answer some of these questions at the confluence of both dark matter detection and quantum sensing, and that once we've proven that this thing actually works, we are going to be deploying it to a wide variety of science applications. I, of course, want to thank the team that's been working on this, particularly Hannah, Anthony, Israel, and Noah, who have all worked really hard to help develop this design, and then, of course, for the support of the whole Fermilab QSC group. Thanks so much.
Thank you, Kelly. Are there any questions?
So I guess in Aaron's lecture this morning, he kind of ruled out dark matter to really have any major particles, like neutron, protons, electrons, at least as a collection. Are there quasi-particles that's really has been effectively ruled out to, at the moment to be a part of dark matter?
So the way I'm interpreting your question is there anything in the standard model, anything that we know about that could potentially be dark matter? Yeah, right. So the answer to that question is no. Everything that we know about in the standard model, including things like neutrinos, right, some more exotic particles that actually have a lot of properties very similar to dark matter. We know that nothing in the standard model checks all of the boxes for all of the things that we expect out of a dark matter particle. So we really are looking for something entirely new.
I just have a question about your light source. I mean, if you're going to detect very, very small amounts of energy, you need to deposit those very small amounts of energy. What light source were you planning on utilizing? And it needs to be very stably controlled, so you know how much light you're putting in.
Right, that's a great question. So for our first sort of just functionality test, we're using just a very simple 635 nanometer laser diode. And then the plan is just to really, really filter the output until we get down to very small numbers of photons, hopefully single photons. And so it's been suggested that we use more advanced methods, something like single photon emitters, like we just heard about previously. That is certainly a really nice solution, right? You can get them on demand and you always get one photon, and they're available in a variety of different wavelengths. That would be great. But the one thing is that this design, one thing that we're really happy about is that it's not that expensive. And it's very, very easy to run. So we're hoping that it's really going to be plug and play, right? We can deliver this device to a new lab and they just get to run with it, rather than having to set up, a whole bunch of expensive lasers or other things. So there's certainly room to improve in the future, but this is what we're starting with.
Great, thanks. Are there any other questions? Oh, yes. Is it easier to access them? So Matthew asks, yes, can this design be made smaller? Would arrays of these systems be suitable to enhance your sensitivity?
Yeah, that's a good question. So actually, one thing that we worked really, really hard on is to make this design as small as we possibly could. That's because, dilution refrigerators are small. There's really a space premium. And so we tried to make them as small as we could. But it turns out that it's really challenging. There's a lot of other design challenges that I didn't talk about today, things like making them light tight, and you want to have everything adjustable so that you can align all of your optics and your mirrors to make sure that everything is working exactly as you expect. So I think that it's maybe possible to make it slightly smaller, but I don't think we'd be able to make it a lot smaller than we do now. One of the other big constraints is that since you're working with deflection angles, your scanning distance is set by your lever arm between your mirror and your scanning area. And so you actually want that distance to be relatively long. And so that's why we do that Z-zig to zigzag. Yeah. Would arrays of these systems be suitable to enhance your sensitivity? I don't think I fully understand that question. We certainly are looking forward to deploying more than one. Potentially you could even deploy more than one in a fridge if you can fit them. But they should operate such that they don't introduce any parasitic backgrounds into other devices in your fridge. So you could run more than one at a time. The other question about dark matter, are black holes dark matter? This is a very common question. And actually, I think it stems from the name dark matter, right? Black holes also dark. The answer to the question is that as far as we know, black holes are not dark matter. And we actually call dark matter dark because it doesn't interact with light very well, right? Light just passes straight through dark matter. So it's actually more aptly called invisible matter rather than dark matter, but that sounds a little less mysterious. So.
And our final speaker today is Demid Sinichev. And Demid is a postdoc at the University of Purdue in the Elmore School, in the Elmore Electrical Engineering, Elmore Center of Electrical Engineering and Computer Engineering, and he works with quantum optics and single photon emitters. So when he's ready, I'll let him take it away.
Yeah, nice. Okay. So yeah, hi everyone. I'm Demid, and I'm a postdoc in Professor Vlachlive, Delsasoa, and Professor Yongchen group here in Purdue. And I'm Today, I'm going to present two of the ideas which I'm going to realize in our group, which are related to the topic of solid-state single photon emitters. So, as you know, any optical quantum system for application in quantum information science in general can be presented like it's depicted here. When you have like a certain number of single photon sources and a certain number of single photon detectors for detecting your state of light, and linear optical interferometer. So, which is basically, and modern interferometer. And it covers almost all tasks in quantum computations and quantum repeaters, quantum communications, which you can do with this system. So the most important part here is this single photon source. It required to be the source of indistinguishable photons, which means that all photons emitted by them should possess equal spatio-temporal mode, and they should be identical in frequency and polarization and all other degrees of freedom which you can consider. So there are two main approaches for single photon sources. The first one is through spontaneous parametric gun conversion, which can be realized through nonlinear optical processes when one photon splits into two. The second approach is with single photon emitters like atoms, solid state emitters, or quantum dots. So with single photon emitters, getting indistinguishable photons is harder, but at the same time, it provides a way to create a deterministic source of quantum states of light. And also it possesses quantum memory property, which is very important if you want to build more universal quantum photonic devices, which you can apply for a big amount of applications. So as I said, today I will focus on single photon emitters in solid states. So as I said before, indistinguishable single photons should be equal in all the degrees of freedom which you can measure. And their key effect, which you can observe with identical photons, if you send them on a beam splitter, symmetrical beam splitter, which half reflects and half transmits light, you can see an interesting phenomenon when both of the incoming photons going only into one of the outputs of the beam splitter and goes into only one detector. So this effect is so-called Hongo-Mantle effect, and this is occurs because of interference, quantum interference between single photons. So if you have distinguishable single photons, you can have a situation when both of the photons can go separately, and this is not interesting. This is classical, and in this case, we will not see any good phenomena which we can apply for quantum information science applications. So with solid state quantum emitters, the problem that they're very strongly interact with medium. And that's why each photon emitted by a single photon emitter, it's slightly shifted. And this produce distinguishable photons, which can be used for our applications. So here you can see example of, in the center, one of the most common single photon emitter and its spectra. You see how broad it is. So to roughly estimate how good our photons, we can measure the bandwidth of our spectra, multiply it by lifetime of our photon, like duration of our photon. And if this number is much higher than 1, it means that it's far beyond the Fourier transform limit. It means that most likely our photons are not distinguishable. So, and in this number is even more than 1,000, and so it's very hard to make it work at room temperature. So there are several solutions to this problem. The first solution is most obvious, is to decrease the temperature. In this case, your interaction with media is getting lower, strength of interaction, and it will work, but it's maybe not practical for all of the applications. And also it doesn't affect somehow speed. Sometimes you need to vary how fast you're extracting the photons from the solid state emitter. So the second obvious solution is spectral filtering, but here is the problem that the efficiency of this process is very low because most of the photon will be cut off by this filter. And the last most promising approach, which is widely used and people apply for many kind of emitters, is using Parcel effect, which allows to decrease the lifetime of the photon emitted by single photon emitters. So Parcel effect occurs when you place your single photon emitter in the cavity with Q factor Q and the mode volume V. And the Parcel factor defines the degree of shortening of your emitted lifetime compared to photons emitted without a cavity. So, and the formula for this you can see in the corner of the slide. So it's mainly defined by the Q by V ratio. So the higher the Q or smaller the V, the better Parcel factor. So, and for solid state emitters, there are two main approaches which gives us this Parcel enhancement. So the first is related to photonic cavities, dielectric photonic cavities, where you can achieve high Q, but mode volume is not very low. Alternatively, you can use plasmonic cavities where you have opposite situation, very small mode volume, but Q factor is also very low. So, but the highest achieved Parcel enhancement had been demonstrated for plasmonic cavities. So it was actually demonstrated in our group before. So if we consider in these centers, you can see that time shortening from 1/10 nanosecond to 10/100 picosecond, which is actually good. But at the same time, it's not good enough to achieve indistinguishable single frontals from nitrogen vacancy center at room temperature. So from here, if you calculate the previous figure of merit, which I presented, like a multiplication of bandwidths of the spectra and the lifetime of a photon, the number is still very huge. So how we can achieve even shorter photons? This what I'm going to do. Today I'm going to present two ideas which can help achieve this. So the first idea is coming from nonlinear optics. It is well known that if you send two laser beams into your nonlinear crystal with optical Chi2 nonlinear successibility, on the output you can generate the third beam. And under certain conditions, this beam will be generated at a frequency which is equal to the difference of frequencies of two input beams. This is so-called difference frequency generation process. And the key thing about this that if you will vary the time duration of one of the pulses, for example, on the bottom on the blue pulse, we will make it much more shorter than another pulse. We also can produce short pulse duration for the output beam as well. So because it's determined mainly by the overlapping of these two wave packets. So we can apply this process not only to laser beams, but also for single photon emitters. And we can send single photon emitters instead of one of the lasers. And on the output, we also will have a single photon emitter. And as I said before, because of this time overlapping, the output photon also will have a shorter lifetime. So at the same time, we make a conversion of the photon, for example, for nitrogen vacancy center, which is mainly operates at visible range, we can easily convert to telecom, which considered as much more suitable for quantum communications wavelengths. So this is one of the ideas, and another idea is use for producing indistinguishable photons is applying another effect, which is called stimulated emission. So idea of this is the following: if you send a single photon to the two-level system in its excited states, on the output with some probability, you will have two identical photons. And this is a very well-known effect, and we are widely used it for lasers. It's the good thing about it that it generates indistinguishable photons even at room temperature. And the photon which is emitted on this transition is completely identical to the incident photon. And this is the most important thing here. So we can apply it to a single photon level. Let's say we have our nitrogen vacancy center and we excite it by the green laser to its excited states. And then we send the coherent state of light generated from the laser. And on the output, in this case, we will have this coherent state plus one photon, which is already not a coherent state of light. This is so-called photon-added coherent state of light, which actually possess non-classical properties, which can be used for quantum information science. So, yes. So this is all ideas I wanted to present. So it allows, both of these ideas allows to generate indistinguishable photons at very short time scale, like which determined by the pulse duration of a laser, which can be as small as even 20 femtosecond. So, and good thing about it that it can be used for capturing ultra-fast quantum phenomena at very small time duration, which probably not achievable with any other approaches. Okay, so I think that's the end of my presentation. Thank you very much. And let me know if you have any questions.
Thanks, Demid. Are there any questions from the audience? Morse.
For your second idea, how do you ensure that you only excite one extra photon?
So before this, you should do characterization of your structure, and you can characterize. So it's basically similar to what we are doing when you are measuring, when you're characterizing single photon emitters. You are measuring G2 after correlation function, which has a deep at 0 time delay.
There's one more question up here at the top.
Mm-hmm.
Thank you, Demid. I had a quick question. For the first approach, how do we ensure that anti-bunching is guaranteed from the 4-wave mixer for the difference frequency generation process?
So in this case, your output signal is proportional to like your input signals, and if you don't have a photons, you will not have any output photons in the third beam. Like actually it's protected by the initial state as well. If you are sending single photons, we will have a single photon on the output as well. Yes. Yes, yes. Probably with some noise sometimes, depending on the process, but still it should work.
Are there any more questions? Are there any more questions? If not, let's thank all of our speakers once again. And thank you guys. That's all we have scheduled for today, except for a dinner later tonight. but that's all for the talks. We'll see you guys tomorrow. If there's anything else. And for dinner.